LROC at the Arizona State University, and he's going to be talking to us about seeing into the dark.
Okay, I'm going to be Stephen Koeber today. I think he's on an airplane right now, so he couldn't make it to the talk. So I'm going to review a campaign that we started, or a couple campaigns that we've completed, and one we're in right now, of taking long exposure images so that we can image into permanently shadowed regions of both the North and South Poles. So with that, let's, I guess, go to the next slide. Okay. With the NAC, in certain circumstances, without even adjusting the exposure times, especially along the terminator, we get enough illumination where if we stretch the image, we can actually see into the shadows. And where we can do this where we don't need to adjust exposures are typically on small craters where the sun comes quite a ways down the far wall. But some of the most interesting craters, especially near the South Pole, are very large, on the order of 40 kilometers, 100 kilometers. And in those cases, the far wall is great enough distance from the floor that the amount of secondary illumination is decreased quite a bit. So we have to up the exposure times, and so we end up with these kind of unusual pixels that are very long in the down track direction and narrow on the wide track direction. The aspect ratio can be factor 10 or 20 sometimes. Let's go to the next slide. Okay, this is just an example of Falstini Crater near the South Pole. I believe the diameter is about 40 kilometers. The image on the left was taken in 2009 during the commissioning phase of LROC, when we just did some experiments to get a feel for what we could do and what we couldn't do in terms of permanent shadowed imaging. So the image on the left was at exposure time of 12 milliseconds, which, to put that into context, the nominal exposure is 0.3 milliseconds, so that's about 36 times the normal exposure. And we ended up with, I believe, something like 1 meter by 20 meter pixels, so we resampled it at 10 meters, which is halfway between in that aspect ratio. On the right, and we weren't very happy with the signal-to-noise ratio in that particular image. When we started another campaign in 2012, you'll notice there was a big difference in years between these, because we had other responsibilities that we had to take care of, South Pole mosaics and North Pole mosaics, so that we could not spend the time taking these long exposure images. It's only now that we're in the extended mission where we're doing new science. So the image on the right is where we doubled that exposure time, and you can see we significantly increased the signal-to-noise ratio. In both of these images, you can see a very faint red line, and that's outlining the area of permanent shadow, which was defined in other studies by the, I believe in this case, by the Lola team. Next slide, please. Okay, here's a snapshot of where we are to date in our mapping of these permanently shadowed craters at both the South Pole and the North Pole. Craters that are colored in green mean we have a good, quote-unquote, signal-to-noise ratio, and that ranges from some totally awesome images to ones where you can just make out what's going on. And I'll show you some examples of that in just a second. But you can see we've got a lot of progress on both the North Pole and the South Pole. Our best time to do this is when the spacecraft orbit is nearly in the plane of the subsolar latitude, and that's measured with beta angle, which is the angle between the subsolar vector and the plane of the spacecraft. And when beta is 0, we're in that plane with the vector of the sun, and when we're either at a respective solstice at the North or South Pole, those are our best times for imaging. We're kind of in between those right now, but we're heading towards optimal South Pole imaging. So we've just begun a campaign at the South Pole, and it will come to its peak, I think, in late August. Okay, next slide, please. Okay, here's a really fantastic crater, Mainel, where we were able to image inside. And again, that red circle, or the red line, is the areas of permanent shadow. And you can see in this image that I believe it was about 2 meters per pixel. This is one of our best examples where the light is coming down far enough on the wall to really illuminate the inside of the crater. And again, Mainel is a much smaller crater. It's 14 kilometers in diameter, so that's where we get our best imaging. Of course, what we're looking for are any signs of surface frost, which would be an albedo difference, or any kind of morphologic difference that would be some indicator that the regolith behaves differently inside the permanent shadowed craters than in illuminated regions, and this may be due to volatiles that are sequestered in the regolith. Next slide, please. Here's another example of about a 2 meter per pixel image looking inside Sylvester N. And again, the red line shows the area of permanent shadow. As to date, we have not found any smoking guns in terms of, wow, there's a glacier, or any really unusual morphologies that would indicate large amounts of subsurface ice, but we're still looking and we're still excited about it. I don't know if everybody's followed the results from the Messenger mission. There was a really interesting paper that came out early this year. I think it was early this year. Greg Newman was the first author, and it was from the MLA, the Messenger Laser Altimeter, or maybe it's Mercury Laser Altimeter, that looked at albedo measurements inside permanent shadowed craters on Mercury. And of course, the laser is always looking at 0 degrees phase angle, so you get a good measure of the reflectance. And in their data, it was very interesting that in some of the craters that had been shown to be anomalous from the Earth-based radar measurements, they saw high reflectance or high albedo returns. But more interestingly, in even more of those anomalous craters, they found low albedo, low reflectance. And that's something that we're looking at. We're going back and looking through all of these data to see if we can see any albedo change that correlates with that permanent shadow boundary. And we haven't found any yet, but we've still got a lot more craters to look at, and we've still got a lot more imaging to do. Next slide, please. Going back to the idea of albedo contrast, since light is so diffuse inside these craters, it's kind of weird to think about it. It's very different than the sun being overhead, and the sun is essentially a point source. You have a great big arc that's giving you sun coming in, or secondary sunlight coming in from many, many different angles. So it's kind of hard to think about exactly what you would expect to see. So we were worried that maybe albedo contrast would be suppressed, particularly since we don't see a lot of albedo differences within the craters. However, we do see in some of the very small impact craters, bright ejecta, which is more or less just a maturity difference, that we can detect at some level in these types of weird illuminations albedo differences. So again, we're working this problem. And I know that the Lola team is also looking in their data from of reflectance in the permanently shadowed craters. And there was a paper, I think Maria Zuber was the first author about 2 years ago, looking at Shackleton Crater, where they thought that maybe they saw some suspicious albedo anomalies. Okay, next slide, please. Okay, one of the things that we've also found is that in areas where it's doubly shadowed, in other words, where you get light coming in, bouncing off of one wall, and then say it hits the central peak of a crater, there's going to be a shadow of that secondary illumination, so it's a doubly shadowed area. We're not able, there isn't enough light in those so far for us to get any useful image data. And in our map of coverage, where we have poor imaging, it really corresponds in many instances to the coldest areas as mapped by the Diviner team, and those coldest areas are where you would expect them to be in these doubly shadowed areas, because it gets the least amount of solar energy, incoming solar energy. So it's not that this is a discovery on our part, but it's just nice to see that these two data sets are giving the same answer. Next slide, please. Okay, we're trying to improve our ability to predict the amount of illumination in a particular crater so we can optimize the integration time. We want to keep the integration time as short as possible, because the longer you have integration time, you degrade the resolution. But we also want to get signal-to-noise ratio. So we're always walking this fine line of having a good signal-to-noise ratio and the highest possible spatial resolution. And that will be particularly important if you're looking at the reflectance of the ejecta of small impacts inside these craters, or any other smaller size features that might be of interest. We have not really identified any reflective anomalies yet that can be attributed to water frost on the surface. And as I mentioned earlier, we get the strong correlation of areas we can't image into with the temperature maps published by the Diviner team. So this is really a progress report. We have a lot more work to do, and perhaps next year we'll have some more concrete results. With that, I will say thank you.
Great talk, Mark. This is actually really exciting work. Barb Cohen has a question. Says, how do you determine the true albedo within the shadowed regions since the light is coming from scattered sources? Is it relative to the outside of the shadowed region?
Well, we haven't determined any true albedo yet. Yeah, it's I think, Barb, clearly you can see that as a problem. The easy way to do that would be if you had an image where you could successfully see the illuminated portion and the non-illuminated portion. And then in most of the images we can't do that because we get saturation in the illuminated ground. However, in these small craters, you can actually see inside the crater and outside. And that's how we can establish a link with the reflectance on the outside. However, you hit the nail on the head with the problem of that diffuse illumination. So we would have to make up some sort of model or standard that corrected for that. And we haven't gotten that far yet. But if you want to help on that, that would be fun.
Great. Thanks, Mark. And I was kind of curious, do you have any plans to correlate any of this really neat crater data to what's coming out of the mini-RF and the search for water ice with that instrument as well?
Yeah, that's where we're really concentrating most of our analysis right now and targeting are on, there was a Sputus paper that came out. It's really terrible when you can't remember years anymore, but it was like 2 years ago, and they identified these very interesting anomalous craters near the North Pole. They're typically smaller size, and they had a strong radar roughness signal inside the crater, but it was just normal on the outside. And so they pointed this out as being very interesting, and they didn't see very many of these class of craters away from permanently shadowed regions. So there is something that's related to the radar signal with these permanently shadowed craters. And so, of course, we've really concentrated on making sure we get the best possible imaging for those, and looking through the imaging data and looking for morphological differences between the inside of those craters and their ejecta blanket, and then also going and looking at the craters that Paul called out in that paper as being normal, and these are fresh Copernican craters in the same area, and looking to see does the roughness inside and outside on the two classes of craters tell us anything about what's going on the inside, and we're really early into that study.
Very cool, very cool. If there are any other questions for Mark/Stephen, that would be great if you could take it over to the general chat. And thanks very much, Mark. We're going to go ahead and move on to the final talk of the session.